I want to welcome you to my lecture today. Today, we're actually going to continue from the variants of logistic regression that we started on Monday. I actually call this variants of logistic regression part 2. Those of you online, I need you to confirm if you can hear me clearly. Is everyone hearing me clearly?
Yep.
Okay, thank you so much. Thank you for confirming that. Uh, Before now, I introduce you to logistic regression. We use logistic regression when the response variable is categorical with levels. And I think I justified in this class the reason why linear regression cannot be used. Now, I walk you through what we call binary logistic. The binary in the sense that we got two levels of the response. Then from there, we move to the variant of logistic regression that I actually call ordinal logistic and the multinomial. That was what we did on Monday. We use multinomial logistic regression in a situation where we got more than two levels for response and they are not ordered. And of course, that's for the multinomial. But for the ordinal logistic, of course, when the levels are more than two, the levels of the response, and they are ordered. Okay, what is new today? What is new today is we got another variant of logistic regression that we call beta regression. I'm going to walk you through when do we use beta regression. I think I've already had, a review on logistic and invariance. Now I want to focus on beta regression now. Okay, now let me tell you this. When do we use beta regression? We use beta regression when the response variable is actually a rate or a proportion. I'm going to say that again. If the response variable, okay, it's not categorical, it's not continuous, but it's something that is in the interval 0, 1. The one we considered before was actually 0, 1. 0, 1 is different from the interval 0, 1. So which means if I want to talk about proportions or I want to talk about rates, okay, then the appropriate regression type to use is actually what we call beta regression model. So if you use a the conventional logistic regression for that, you're actually going to mislead. Of course, I wanted to take a look at what I'm going to show you now. There's a particular distribution in statistics that we call beta distribution. In statistical theory, okay, in statistical theory, we normally have what we call, beta distribution. Give me 1 second. I'm going to grab something. So, like I said, in statistical theory, we have what we call beta distribution. Okay, I want to believe those online can see what I'm writing on the board, right? That's already confirmed if you're seeing what I'm writing on the board, those of you online. Oh, the person said the camera just moved. Okay. I'm gonna rewrite that so that you can see. Okay, so this is beta distribution. Okay, now the beta distribution the distribution is defined as f of x equal x raised to the power alpha minus 1, 1 minus s raised to the power beta minus 1, divided by gamma alpha plus beta, divided by gamma alpha, gamma beta. Okay, we are the alpha and the beta here, they are the shape parameters. Okay, this distribution, we use this distribution when let me be using y because we're focusing on the response. I'm going to be using y, and the range of y in this distribution is 0, 1. Is y lie between 0 and 1. Okay, is a proportion. Okay, so when I'm trying to this very distribution has been proved to be flexible depending on the values of the parameters. And that's exactly what I'm trying to show now. If you take a look at what I have here, okay, in statistical analysis, we normally want distribution to be flexible. When it is flexible, that distribution has a higher chance of capturing, dynamic real life situation. Okay, because of that, we are now trying to incorporate the idea of a beta distribution into regression modeling, so that in a situation where the response variable is actually rate or proportion, we're basically going to use that. Now, take a look at what I'm trying to show now. If y follow beta distribution, this is the density. The other time when I was writing on the board, I was using alpha beta. It doesn't matter. You can use P and Q. You can use A and B, provided they are the parameters of the distribution. Now, when you take a look at what I'm displaying now, this is what we mean by beta distribution. And of course, the parameters P and Q has to be greater than 0. Okay, has to be greater than 0. And the Ferrari and Cribari Netto 2004 proposed what I call a parameterization of that, what they did, because for them to be able to use this as an idea in regression modeling, that they need to reparameterize this distribution. Now, when you take it, when you set mu, because when you set mu to P divided by P plus Q, why are we setting mu to that? Because the mean of a random variable that follow beta distribution is the ratio of P to P plus Q. That is the mean. That's the average. If y follow beta distribution, and when I have mu equal P divided by P plus Q, if I let phi to be P plus Q, of course, what I'm just going to do here, I'm actually going to plug in mu anywhere I see P divided by P plus Q, and anywhere I see P plus Q, I'm actually going to plug in phi. With that, I have a parameterization of a beta distribution. Now, without this parameterization, it may be difficult for us to actually incorporate that into regression modeling. Okay, so that is just the statistical architecture of that. Now, mathematically speaking, the mean of a random variable y that follow beta distribution is P divided by P plus Q, and the variance of a random variable y that follow that follow beta distribution is PQ divided by P plus Q all squared into P plus Q plus 1. We've already derived this in statistical theory. We are only telling the world, if I'm talking about response variable y is a proportion, is a rate, how can I tell about the average? How can I tell about the variance? Okay, Now we want to incorporate that into regression modeling. When we're incorporating that into regression modeling, initially we started with P and Q, right? We started with P and Q, which are parameters of a beta distribution. But Ferrari and Cribari Neto 2004 parameterized that. We are using the mean of the response variable y, which is p over p plus q. Anywhere you see p over p plus q, is basically going to plug in mu, and anywhere we say phi, everywhere we see p plus q, we're going to plug in phi. This is what we have now. We now have new parameters. What are the new parameters that we have now? We got mu, we got phi. Those are the two new parameters that we have. Now, we are actually going to impose a condition on the new parameters that we got. Where the mu is going to be from 0 to 1. Okay. And if mu from 0 to 1, don't forget initially y follow, we can write y follow beta distribution with a new with parameter mu and phi. Okay, then we can say the expected value of y, which is the mean, is going to be equal to mu. The variance of y is now going to be this guy here. And of course, the parameter phi is what we call precision parameter. Okay, that's what we call precision parameter. And there's something I say here: for fixed mu, the larger phi, the smaller the variance of y. And the phi raised to the power minus 1 is going to be a dispersion parameter. You remember the other time, because we're actually going to expect a violation of constant variance, the idea of a weighted least squared is what we're going to use, because we don't expect this, the response variable to have the same variance given different predictor. Okay, we don't expect that when the distribution of the random variable is non-normal. The distribution of random variable is non-normal. But you know what? In terms of regression model, this is what I'm going to talk about. Do you see G of mu I equal to S transpose beta, right? I actually want to write that in terms of regression model. Okay. Okay, that is just the statistical theory, but you don't need to worry about that. But I'm just going to tell you something now. Take a look at equation 1, equation 2. Equation 1 is the variance of yi. Why do I say variance of yi? Because the variance of the observations are not going to be the same. The variance of y1 will be different from variance of y2, and so on like that. And of course, in terms of the mu and phi, this is the variance of yi. And that very mu, don't forget, mu is the mean function of a model, which is basically S transpose beta. You remember here, I said the G of mu I is S transpose beta, and that was why I'm actually trying to, what I'm plugging in here, I'm only plugging in, I'm trying to say that very mean function depends on, the linear combination of parameters. Well, when I say parameter, I'm talking about the regression parameters now. The beta that you see is talking about regression parameters. Okay. And if I want to estimate the parameters, which means if I want to estimate the parameter, the phi and the mu, then I'm actually going to use the method of maximum likelihood. The method of maximum likelihood requires that I should get the likelihood function. I should take the log of the likelihood. Then I differentiate. I set that to 0, and I actually solve for the parameter. But what I'm just explaining to you now, you don't need it. I'm just trying to tell you what we do behind the scene in statistics. But I'm going to tell you where it concerns you now. Let's come to application. Okay. Now, I just walk you through the statistical theory, which is more or less the foundation of how we derive the beta regression model using the underlying distribution of beta distribution. But this is where it should concern you. Take a look at what we want to do now. We actually want to go into the basic model, estimation, inference, diagnostics, just like what we used to do in the conventional linear regression. Okay, now let's take a look at an example. The variable, if the variable of interest is yield, and the yield is proportion of crude oil converted to gasoline after distillation. Let me tell you this. For those of you who have the idea of chemistry, or you've done some distillation before, it is not all gasoline, or all crude oil that will be converted to gasoline. Okay, so which means that is where proportion is going to come in. Okay, we're talking about yield now. What is the proportion of crude oil that get converted to gasoline? Of course, United States is one of the oil, in fact, the largest oil producer in the world. Of course, they into this where they convert the crude oil into gasoline, but it is not 100% of the crude oil that is being converted to gasoline. Because of that, we're talking about proportion here. Okay, and if I want to model this subject to some factors that I'm actually going to call independent variables, explanatory variables, that we also call predictors. You know what we're going to do? Because of the fact that the response variable is not categorical, the response variable is not continuous, but the response variable here is a proportion. We're basically going to use beta regression. Now, there's an example now. That's why I said the beta regression model for rate and proportion. If you have been using a different model in your research for, to model a response variable that is proportion or rate, you are wrong. And that's why I'm actually introducing to you an appropriate model that can be used that we call beta regression model. Okay, now take a look at that. Now, another example, apart from the gasoline, is the proportions of individuals infected with XYZ when exposed to various levels of artificial preservative agents. Let me tell you this. With due respect to those who died due to COVID, all of us were exposed to COVID, right? And it is not all of us that fall sick, and not all of us, that actually died at the end of the day. So which means here we proportion, this is more or less talking about proportion. Okay, now I wanted to focus on the screen now. If I actually want to run beta regression in R, what kind of package do I need? You need a beta reg. This is beta reg. Okay, you need to install a package called beta reg, and you also need to load that beta reg. Okay, now if you want to have access to my data that I want to use, okay, the gasoline data that I talk about, okay, if you load the package beta reg, you're actually going to have access to that data. You know what we want to do here? We are looking at the effect of batch and temperature on the yield. Don't forget, those who actually are into fractional distillation in chemistry, or those who actually convert crude oil, okay, into gasoline, I know they're basically going to subject the crude oil to temperature. Does that make sense? Maybe high temperature. And that's why we're looking at the effect of temperature on the yield. Not only that, we're also looking at the effect of batch. Situation where you got so many batches, okay, and is there variation in batches? Okay, so here, if you take a look at there, you can see beta reg, right? When you are running linear regression, it's going to be LM. When you are running, ordinal logistic, binary logistic, or multinomial, of course, you're actually going to have a different syntax. The one for binary logistic is going to be GLM. The one for multinomial is going to be, I think, POLYR or something. And the one for multinomial is actually multinom. But right now, I'm actually specifying beta reg. Okay. When we do this summary, let's look at the results. Okay. This is the result. Oh my God. Look at the result now. The result is actually looking like the output you are familiar with. Okay. Now let's take a look at this result. Looking at this result now, you can see batch 1 to batch 9, right? The fact, if you have batch 1 to batch 9, it means you've actually worked on 10 batches. Arrow will automatically coded one as 0. You get what I mean? So we got 10 batches, and that's why you're only having batch 1 to batch 9. Look at the temperature and take a look at the p-value now. That measure the significance of each of that. Okay, this is the output of a beta regression. Any question on this output? Any question on how the beta regression is being implemented in R? Is there any question on how that is implemented? Any question? Okay, now if you guys are good now, okay, so what I'm actually, of course, you can see all that. Now the next thing I want to do, I want to consider what we call, because, if you take a look at what I have here, this is not this is not as appropriate in a way, because of the fact that we may want to see whether we can improve on this model and try what we call a variable expansion model. I said, although the beta model already incorporates naturally a certain pattern in the variances of the response, because let me tell you this, the conventional assumptions of linear regression is violated, which is the assumptions of constant variance, even though the beta regression has the statistical architecture of a beta regression has already incorporated the fact that there's going to be a violation of constant variance. Okay, so, but it is also necessary that we incorporate further regressors to account for heteroscedasticity, okay, as suggested by Simas et al. 2010. Now, because of that, I wanted to see a change in the code now. Okay, the change in the code is more or less like, I'm actually going to write the batch plus the temperature, and I'm actually going to write a vertical bar temperature, because the temperature is the main important variable in the distillation process. I need to identify a variable like the explanatory variable, the one I actually feel that is the most important one. Okay, and I will be guided by literature. If I want to do that, don't forget, I'm trying to look at the proportion, what actually determine the proportion of crude oil that get converted to gasoline. The main important variable is the temperature. And that is why you see the vertical bar temperature. What am I actually doing here? I'm actually incorporating the vertical bar temperature, to further, it's like I'm incorporating further regressors. Why am I doing that? To account for heteroscedasticity. What do I mean by heteroscedasticity? Heteroscedasticity means non-constant variance. Okay. Now, when I incorporate that, okay, the result you're going to see, you're only going to see the temperature only. What is the p-value? Take a look at the p-value. It is significant. Okay. When you consider this guy now, that vertical bar temperature, the only way you can see whether there's an improvement is when the p-value associated with that temperature comes significant. And that was why I said that signal a significant improvement by including the temperature regressor. Take a look at that. Now, do you know that now I got two modules? The first module is when I did not incorporate the regressor temperature to correct for heteroscedasticity. And this is the second one where I incorporated that. Do you know I can use the idea of what we did before, like the ANOVA, the nested ANOVA test? Oh my God, take a look at this. I'm back at the likelihood ratio test where we compare between two modules. What is the first module? The one I call the GY logic is the first one that we fitted. This guy here, right? That led to this, that actually led to this. The second one that I call the GY logic 2 is the one that I incorporated regressor temperature to actually account for heteroscedasticity. Take a look at that. Now, you know what I want to do now? I want to choose between the two modules. Which one is great? Okay, then I'm actually going to use the idea of a likelihood ratio test. And I'm just going to write LR test into the first module and the second module. Don't forget, the first module is the simpler module. The second module is the complicated. In the end, now if you take a look at in the null hypothesis, the non-hypothesis is actually going to support this guy here, and the alternative is going to support that. Take a look at the p-value now. I got it 0.037. A 0.037 is less than a 0.05 level of significance. And what does that mean? And I said this can be interpreted as testing the non-hypothesis of equal dispersion against a specific alternative of variable dispersion. So which is trying to say in the module one, you are trying to talk about equal dispersion. Like equal dispersion means equality of the variance. So which means using this guy here, you are assuming equality of the variance, but using this guy here, you are trying to say there's no equality of the variance, and that is why you are incorporating the regressor temperature to correct for the heteroscedasticity. But what you can see now, the p-value is actually less than 0.05, which means you're actually going to reject the non-hypothesis. Rejecting the non-hypothesis, what does that mean? The second module is more appropriate. Any question? Because you know why? When you are working with a categorical response variable, or a response variable with proportion, or the response variable with the rate, there's always going to be violation of constant variance assumption. Does that make sense? Okay. Now, I want to go into another example. Now, I want to go into house food expenditures. Okay, the house food expenditure data for 38 household. The dependent variable is food divided by income. Take a look at that. You know, when you see food divided by income, you know what that means? The proportion of household income spent on food. If you spend everything on food, what's going to happen? That ratio will be 1, right? But that ratio can never be 1. That ratio will always lie between 0 and 1. Because of the fact that you can never spend, okay, let's say you don't spend anything on food. What happens? That becomes 0, right? If you spend everything on food, that ratio becomes 1. That's an extreme side. It can never happen. It's always going to be greater than 0 and less than 1. And that is what makes it a rate. That's what makes it a proportion. If I now want to link this now to certain risk factors, two explanatory variables like household income and the number of persons in the household, okay, you cannot use a linear regression here. You cannot use a logistic regression here, but the appropriate regression is the beta regression, because the range of the response is in 0, 1. Oh, those of you online, can you see confirm if you're still hearing me clearly? Those of you online, can you see confirm if you're still hearing me? Okay, thank you so much. Now, I want to load my car package again, and I want to work on this data, the data on house food expenditure. The response variable is a ratio of income spent on food. and the explanatory variable is the household income and the size. Okay, the number of person living in the household. Okay, now the very first thing I'm actually want to test is, let us test whether the constant variance assumption hold. At times it could be violated, at times it may not. That depends. Now, right now, of course, you know what we did in class. We're going to use Breast-Pagan test, right? We're going to conduct a Breast-Pagan test, okay? And the Breast-Pagan test actually giving us 0.051. But what is the model? This is a model. If you want to have access to your data, you need to load. There's a lot of data set that come. Those of you that are looking for data for your projects, do you know that there's a lot of data in R? There's a lot of data that come with the R package. The only thing you just need to do is just to actually load an appropriate package for you to have access to that. Now, do you know, if I want to have a data, if I want to get a data now on the food expenditure, I just need to load the package beta reg. When I do that, now I want to run the beta regression now. What am I doing here? Okay, do you know why I'm actually you know what I'm doing here? I want to fit inappropriate model false. What is the inappropriate model? Fitting linear regression. Do you see LM? That's a linear regression. Okay. Now fitting linear regression for this. Okay. I know if you take a look at some of the papers around, some have misled the populace. Because when you use the wrong statistical model, you're actually going to have a wrong conclusion. It's like a garbage in and garbage out. Now, you can see LM. I'm fitting linear regression for this. Let's see the result. This is the result. Somebody will start celebrating here. Oh, the income, the p-value is significant. The person is significant. Take a look at that. But that is not an appropriate model to fit. I told you the other time. The fact that a court in California tries somebody that commit an offense in Minnesota, if that court was able to establish the truth, whatever decision they take is null and void, because the California court does not have a territorial jurisdiction, even though the linear regression returned a significant result. That doesn't make it appropriate. Does that make sense? Now, when I go for the other one now, this is now fitting beta regression model. But do you know what I'm fitting here? I'm fitting beta regression model, and I'm incorporating another regressor. Look at the vertical bar persons. We know somebody may argue that. Why not income? I can try the two. I can try for income. I can try for persons. Take a look at that. If you take a look at the first two, what I'm trying to do here, if you look at the likelihood ratio test that I'm conducting, the first module is when I just fit beta regression, where I did not incorporate a vertical bar, where I'm actually taking equal expansion, right? But the second module is when I actually incorporate a vertical bar person this time around, and what happened in the end. Take a look at the p-value. The p-value is 0.0055, which is less than a 0.05 level of significance. And because of that, I'm actually going to reject H naught. Rejecting H naught, okay, rejecting H naught has already suggested to me there is nothing like equal expansion. Okay, so take a look at that. So I've already assumed, the FE beta 2. I'm gonna write something here for those who are online. This guy here for those who are online. Okay, the I'm still gonna write it on the board. The FE beta here, okay, is it's gonna be less than minus beta reg, okay, minus beta reg, okay, into one food, okay, divided by income, okay, and I'm going to regress that on income, okay, plus persons. That is what I mean. For those of you online, I'm still going to write that for those in person. So this is FA beta. In the FA beta that I faded, there is nothing like this guy. Okay, but the FE beta 2 is when I incorporated persons. Okay, because let me tell you uh, the amount of income you're going to spend on food depend on the number of people, greatly depend on the number of people you have in your household. Because you already have your income. That's why I'm not considering income. Even though income is one of the factor, but the one that could cause disparity, I'm talking about the variable that could cause huge disparity is the persons, depending on the person you have in the household. Now, for those of you in the class, what I just put on the Zoom, for those online, is you're going to be wondering, where do I see in the LRTS, you can see FE underscore beta and comma FE underscore beta 2. And what you can see on the board, right? What you can see is the FE underscore beta 2. Where is FE underscore beta? So for those of you here is FE underscore beta, okay, is actually less than minus beta reg, okay, beta reg. Okay, the beta reg, income, one food income, and that is basically going to be in relation to income plus persons. That is a simple model without the vertical bar person. Does that make sense? That's what I mean. Now, the takeaway from here, give me 1 second. I think a chat came in. Oh, okay. Now, the takeaway from here is that the non-hypothesis of equal expansion is rejected, right? Why is it rejected? The p-value here is less than 0.05, and which actually means our conclusion will be in favor of the complicated model which is model 2, where the body model 2 is going to tell you there's no equal expansion. Okay, now take a look at this guy now. If I want to get another way to look at it, if I don't want to conduct a likelihood ratio test, I can fit the two model separately, one at a time. Then I'm going to get the AIC. Look at that. What am I doing now? Okay. I may want to get the AIC or I want to get the BIC. Like what I'm finding here is finding the BIC. How is this one become a BIC? Don't forget in the BIC, then it is K equal to log. You remember that in BIC? Okay. Now take a look at it too now. Okay. Which one has the lower AIC or BIC? Is it the second module, right? You see, negative 80.182 is smaller than negative 76.117. And that was why I said there's evidence of variable expansion. Okay, and model FE underscore beta 2 seem to be preferable. Don't forget what caused the variable expansion here is the numbers of persons in the household. Does that really make sense to you? I told you the other time, our module are doing great. It's not as if our modules are failing us. Our modules are not failing us. We are the one that we're not using an appropriate module. The modules are fantastic on their own. The only thing we just need to do is trying to use an appropriate module for a given situation. So what I just demonstrated to you today is the use of beta regression model when the response variable is a rate or proportion. Okay, you cannot use linear regression. You cannot use logistic regression, but you can only use beta regression. Do you know this beta regression is kind of new, introduced in 2004? Very new. Okay. Okay. So now let me now tell you something. Even do you know that uh, we have different link functions? For instance, if we want to improve on our model, on the beta regression model, just like something that we did when we are dealing with the linear regression, like we always look for a way out to improve on our model. Why do you think we need always want to make sure we improve on our model? Because every statistical model has an error. No matter what we do, error can never be forced to zero. And that is the reason why there's always going to be research. That's what we're talking now. Research is going on. Or what they are trying to do is to be able to have an improvement on the error. And having an improvement on the error is like you are making an effort to reduce that, but there's no amount of effort you're actually going to put in that will make it zero, which means we're always going to have a way to improve. Now, let me tell you this. The link function in relationship, particularly in when we are working with the situation where the response variable is categorical or is a rate or is a proportion. Okay, we actually need to choose a link function that is basically going to be appropriate, and that was why we have a different link functions. I said, as in the binomial GLN, selection of an appropriate link function can greatly improve the model fit. And this was actually given by, this guy and Neda in 1989. Okay. And, especially if extreme proportion is close to 0 or 1, imagine you are working with a data where the rate is very high or the rate is very small. You know what I mean by very high? You are getting something very close to 1. It's 0.9, 0.8. That's very close to 1. Or you are getting something like 0.000 something that's very close to 0. When we are talking about the extreme values for the proportional rates, that we need to be able, if we want to improve on the quality of our model, then we need to consider different kind of link functions. I'm talking about in a extreme situation. Now, because of that, I wanted to take a look at, but what do we mean by link function? Link function is more or less like, can I have a transformation way? Since I know there's a problem, right? Now, the first model here, look at the first model. Okay, I didn't specify any link function, which means I'm using the conventional one. But when you look at the second one, what do you see? Log. You remember when we were dealing with the power transformation, okay, that we always use log of this, that. Now, in a situation where I introduce a link function that has to do with the log, and the one that I don't introduce that, how do I know which one I'm actually going to go with? Do you know I can just look at the pseudo R squared? Okay, we're going to look at the pseudo R squared. If you take a look at the pseudo R squared, it's more or less like the R square we know, but this is the name we call it when you are looking at the categorical response variable or proportion or a rate. Okay, now take a look at the first one, the pseudo R square 0.96, but take a look at the second one is 0.98. That's an improvement, right? When I use a link function log. Okay, now when you take a look at this one now, what if in a situation I got 3 different models? Oh my God, I'm going to tell you the first model. The first model is when I look at the effect of temperature and bash. What am I assuming in the first model? Can somebody tell me? I'm assuming equal expansion, right? Equal expansion, right? You did not see any vertical bar, right? But take a look at the second model. In the second module, I'm using the same link function as the first module, except that I'm actually incorporating regressor temperature to be a dispersion variable. Can you now see the third one? What is the third one talking about? This is when I did not introduce any dispersion variable, but the only thing I introduced is the link function, log. Now, how many modules do I have now? I got 3 modules. And when I have 3 modules, do you know, I can do the AIC of all the 3 modules. Not only that, I can also perform the likelihood ratio test. Now, when I do the AIC of all the 3 now, oh my God. Oh my God, take a look at this. I'm actually going to choose the module with the lowest AIC. Which module is the module with the lowest AIC? Is the one that have the log. Look at that. Oh my God, end of story. Is there anyone who want to ask question about the beta regression model that we introduced today? Any question? Go ahead. That's it. That's a look at me. Look at me. Send me a message for extra credit. If I hear you correctly, you are trying to say somebody has in the class. Can we also use the the link function log for the one with the vertical bar? Is that what you mean, right? Yeah, you can do that. In that one, you know what you're trying to do, but when you do that, that is too much energy. You know why I call that too much energy? Too much energy is like you have a lot of intervention. You know when you introduce a log, you are transforming. You don't introduce that, there's no violation. And at the same time, you are now still incorporating a regressor, yeah, as a dysfunction. It's like that's a double way, but that may look too expensive, but it's something that we can also consider, but it's too expensive because don't forget we don't have time. Well, so we believe that if we just instead that we introduce a leaf function, a new leaf function, or if you don't want to introduce a new leaf function, then we can just leave it as introducing a regressor that can act as a dispersion variable. That's a good question. Okay, now when you take a look at this now, you basically say that the one with the log without even incorporating. So which means this is takeaway. When we get the leaf function right, okay, when we get the leaf function right, there's possibility that we've already addressed the violation. It's just like somebody is sick and we're making a lot of efforts to get a person back on track. That is what we mean. Okay? But we need to be careful at times. The effort that we're putting in order to avoid overdose. When I give the person two doses and I say, okay, it's not still feeling fine. Let me just increase that, or let me do. Otherwise, there's going to be issue. Okay. Now, this is beta regression. If your response variable is a rate, it's a proportion. Okay. You need to fit beta regression model. This is going to be the end of my lecture. I also need questions. I need questions. If you want to read more on beta regression, I will advise that you just type that into Google. Just type beta regression model into Google. You're basically going to see a lot of work is going on. Okay. Is there anyone who want to ask a question on this? Is there anyone? Okay. In the absence of question, make sure you stay safe and have a lovely day. Bye for now, everyone.